Okay, so we should probably start while the last people are sitting. So it's a great pleasure to have Sukyoung Yi here for our weekly seminar at IAP, who is hiding there. So Sukyoung has been doing his PG in '96 at the Yale University on stellar evolution, right? And then you did a NASA postdoc from '96 to '98. And then from 1998 to 2001, you've been a research scientist at Caltech and member of the galaxies community. And then you moved to Oxford as a lecturer from 2001 to 2005. And from 2005, you know, a full professor at the Yonsei University in Seoul, in Korea. And so you're also a member of the SAMI survey, spectroscopic SAMI survey, and you work on, and Sukyoung work on semi-elliptical modeling and hydrodynamical modeling of galaxy formation and large-scale structures, and we'll hear about that.
Thank you very much. It's always my pleasure to be back in Paris. I have to say this. My first visit to IAP was in 1998. 1998 was a memorable time. I was kindly invited by Bridget. I don't see Bridget this morning, but anyway, I spent a week here, and that week was the week of World Cup finals. Finals. So I was here as a guest. I didn't have many friends. I saw Joe in the hallway, but and on one of those days in that week, I managed to go to the plaza in front of the Hotel de Ville, and I watched the final game. And guess what happened? France won the World Cup, and I, having no really good reason, marched along with thousands of people on the Champs-Élysées on that evening. So that was the beginning. Hi, David. So after that, I think this is something like 20th visit to IAP. Maybe, I don't know why I'm visiting IAP so much, but maybe the beginning was so pleasant anyway. Yeah. Thank you very much. Today I'm going to talk about the spin evolution of galaxies. It's helped by a lot of people, especially Yohan Dubois and also the Horizon scientists, and also my group members, some of whom are in this room. In the beginning of 21st century, probably the most interesting lesson I learned about galaxies was the fact that the classical morphology-spin connection is frail. So classically, these galaxies are rotation supported, and roundish galaxies are pressure or dispersion supported. And this is what I teach my students. But this connection is a little bit now shaky. In early 80s, Davis et al. Suggested that actually, even among the early type galaxies, there are some fast rotators. So the faint early type galaxies can have some rotational support. We knew about that much, but then Sauron changed everything. So this is a illustration by the SAMI IFU survey. So now with SAMI, instead of getting one integrated spectroscopic property of a galaxy, now you can have pixel by pixel SEDs for individual galaxies. And this gives you postage stamps of velocity curves from Sauron project. Shockingly, Sauron got the IFU data on about 48 early type galaxies, and the majority of them show very prominent rotation. So we knew that there is a rotational component in early type galaxies all along, but probably not this much. So when Roger Davis gave this first talk at Oxford, I clearly remember this. My first reaction was, you must have some problem in galaxy selection. That was my response. But this result has been confirmed and corroborated by continued projects. This one again shows you the Sauron data on 48 early type galaxies, radial profile of lambda, the thing called the luminously weighted spin parameter. So that's basically a rotational speed divided by rotation speed plus dispersion component. And then the blues are the so-called the fast rotators, and the reds are the slow rotators. As you can see, among these 48, the majority seem to be rotating quite fast. And if you look at more recent data from Atlas 3D plus Australian the SEMI, and then now you see lots of early type galaxies actually do have high spin parameter. And it's a little bit tricky how to divide fast rotators and slow rotators, but if you believe some of the suggestions made by Atlas 3D team, and then roughly about 85% of the morphologically early type galaxies seem to be classified as fast rotators. And compared to 1983, Roger Davis et al. Data, now the presence of fast rotators among early type galaxies is much more prominent than before. So now we go back to the first slide about the morphology spin connection. So the textbook, I learned astronomy from used to tell me that there is a very tight correlation between morphology and spin property, but I'm not sure anymore. 10 years or maybe 15 years after Sauron now, I no longer claim to know anything about spin morphology connection. So from the Capellari et al., and now they say even the roundish galaxies can have slow rotators and fast rotators, and then drop spin morphology connection forever. So as one of the theorists, we were wondering what's actually driving the spin property of galaxies in the realistic universe. So basically, in the hierarchical universe, galaxies do merge with each other, and then so people would claim that maybe as you have more and more mergers, chances are that they will lose the ordered motion more. So probably more frequent mergers between rotating disks would lead to, at least by probability, lead to a rounder and less rotating systems. Since that was the common sense, and then that seemed to work quite well for the morphology spin connection, that's why we are puzzled about this IFU data, right? So this is a classical example of Springer et al. That showed the disk mergers result in more spheroidal shaped galaxy. And we have seen this many times, so probably we don't have any more debate on this. So there was some theoretical attempts in the last about 5 to 6 years that try to understand the spin parameter distribution among early type galaxies that presumably are results of some mergers. So can we maintain some rotational properties in merger remnants? That's the question, right? So the first one, to my best knowledge, was done by Sadek Kokfa, now at Edinburgh. And then in his semi-analytic approach, he was able to reproduce the IFU data of slow rotator fraction, or maybe in this case, fast rotator fraction. So now the more massive galaxies are rotating slowly, and less massive galaxies are rotating faster among early type galaxies. And the observational data are reasonably well reproduced by his semi-analytic model with some assumptions, okay? So now, right, so mergers do happen in hierarchical universe, and when you have mergers, there are higher chances of turning disky galaxies into dispersion-supported systems, yet still in the lambda paradigm, it is possible to make the observed slow rotator fraction. So that gave us some hope. And then numerical simulation challenges the same problem. So in this case, Bois et al. And also Jesse et al., they used the one-on-one, the equal mass mergers, and then reproduced lambda spin parameter versus ellipticity distribution. Okay, reasonably well. So the data dots are the Atlas 3D galaxies, and then the shades are the results of the one-on-one equal mass merger simulation using some projection effect and so on. I don't know whether you will take this as a very good match or maybe, but for the first simulation result, probably this is quite promising, I would say. And then quite likely, Moody et al. Now showed that lambda epsilon paradigm can be reasonably well reproduced if high spin galaxies are just binary mergers, whereas just one-time merger, whereas many mergers can lead to rounder and slow rotating early type galaxies. And finally, Knapp et al., he focused on the 44 central galaxies in large groups, and then with some projections and so on, now he was able to stretch out based on these 44 galaxies due to projection effect. He was able to reproduce the large parameter space in lambda epsilon diagram. And this is probably more realistic than anything I have discussed before. So this is a cosmological simulation, one on Eagle, the other one on Illustris. Eagle reproduces some of the angular momentum distribution as observed in IFU studies, and Illustris also reproduces lambda epsilon diagram. This is Atlas 3D, and this is Illustris. It's okay. So this is Zephyr Penoyer's work. So I was curious whether I could reproduce this theoretically. So the first thing I did was I ran cluster zoom-in simulation. So first half of my talk will be about the YZiCS, our cluster simulation, which was done at Yonsei with about 10 million core hours. The simulation was mostly done by my student Ho-Seung Choi here. So by the end of, where is he? So by the end of this talk, if you find this stuff quite interesting, then you should talk to me because he's looking for a postdoc position. Right, so purposely, we use the same baryon physics as used for Horizon-AGN so that we can compare our high-density region simulation with Horizon-AGN later. So we performed 16 cluster simulations, and the mass was up to about 10 to the 15 solar mass. And the resolution is comparable to the Horizon-AGN. So it's a zoom-in simulation, so it's one cluster area. And this is one mock image of one model cluster. So you see spiral kind galaxy, thin and round, elliptical, and bar galaxy, merging galaxy. So it's okay. And so this is a model galaxy, a randomly chosen 3 model galaxies from our cluster simulation. Cluster early types, they appear early types, right? It's a stellar density map. And their rotation curve, rotation map. So this is a fast rotator, slow rotator, or maybe intermediate. And this is dispersion, low dispersion, high dispersion, low dispersion. Rotation profile, very fast rotating, slow rotating. So indeed, in this cluster simulation, we were able to reproduce slow rotators as well as fast rotators, rather realistically. And then we monitor one galaxy and its lambda profile evolution, starting from high redshift down to redshift 0, and their sigma map and the velocity map. We'll probably rerun, yeah. So you can see the lambda profile dances very widely as this galaxy encounters with another galaxy, sometimes pass by, fly by, other times merger, and then eventually this one becomes a slow rotator. But you can see that the spin evolution has been really, really wild. You really need to know the hierarchical merging picture and the history to understand the final product. And finally, from this cluster early type simulation, lambda epsilon distribution appears like this. Blue is the density map of these 1,700 galaxies from our models compared with Atlas 3D data. So our galaxies are too round compared to the observed data, and our galaxies are relatively slower rotating than the observational data. Probably because our galaxies are all coming from massive clusters, whereas most of the observational data are field galaxies. For these cluster galaxies, we see the distribution of lambda epsilon at high redshift, they used to be fast rotator, the blue shades, and then they progressively turn to slower and slower as time goes on. That makes sense. So now I got curious about the origin of the spin change. Okay, so I just showed you that spin actually has been down as a function of time, like that. So now, what is the change, the origin of the spin change? But I earlier showed you that all papers, previous papers, unanimously said it's merger that's causing the spin down on galaxies. So I want to see whether that's true or not. So now I show you the lambda evolution as a function of time this way, and the blue shade shows you the density map of 17 cluster elliptical galaxies, starting from high redshift down to redshift 0. So in the early time, they used to be faster rotator, but progressively they turn into lower and lower, slower rotator. Okay? And on top of these 17 galaxies, now I show you 3 examples. Is it 3 or 2? Yeah, I think there are 3. 3 galaxies that had at least one major mergers since redshift 3. Okay? In this cluster environment, I have many more galaxies, but I'm now showing you 3 just example galaxies now that happen to have had major merger by this criterion. And then now, whenever there is a major merger, this is 1 to 2 merger, and now spin changes. When there is another major merger, there is another spin change. So whenever you have a major merger, spin changes as expected. The problem is the direction of spin change is not obvious. It does not always cause spin down. Depending on the merger geometry, sometimes it spins down, other times it spins up. So it's chaotic. And if you have 100 mergers, probably ensemble average is easier to understand. But if you have only about 1 or 2 mergers in the last 7 or 8 giga-years time, then the result is really not easy to predict. I show you the other case that had minor mergers, not major mergers, minor mergers down to 1 to 50 in stellar mass. And then whenever you had minor merger, yes, they change the spin value, but again, minor merger does not always causes spin down. Sometimes it spins up, other times it spins down. And now I show you galaxies that did not have any merger since redshift 3. And then these 4 examples, they still spin down. Just like major merger galaxies or minor merger galaxies, they continue to spin down for some mysterious reasons. Just like the other galaxies that did not, the other 1700 galaxies. So based on this, I'm forced to think that mergers have really important impact, but there is something much more than mergers that drives the spin evolution of galaxies. So now I show you in a slightly different illustration. So that's the distribution of a spin change, delta, lambda, and relative probability for all 1700 galaxies. So what I did was, whenever a galaxy had a merger, either major or minor merger, I measured the spin change, okay? So typically speaking, say this, the red curve gives you the distribution of spin change caused by major merger. And there were altogether about 504 major merger galaxies, and the number of events was 628 events, and then the distribution in spin change is about this. So they have marginally negative impact on the spin. That means now ensemble average says major merger will cause spin down, but just a little bit. And minor mergers, the same. They cause a little more spin down than major merger simply because they are more numerous. But if you combine minor merger and major merger, that the combination does not explain the total spin down, the black curve. Actually, something other than major or minor merger was behind the total spin change. That's what it says. This diagram is a little bit tricky to understand, but anyway, I'll show you one example. This diamond, 6 diamonds, gives you one example galaxy. The total change for the, about several giga-years was about minus 0.4. That's the, actually that's 0.3, right? The black. That's the total change of spin. So it has spun down this much, and it had 3 minor mergers. 2 of them caused the spin down, 1 caused the spin up. It had 1 major merger, actually, which had caused the spin up. And whatever that is, something other than major or minor merger caused much more spin down. As a result, now you had this much of spin down. So mergers obviously are important, and it could be very important in some environments, but there is something other than merger that could be even more important than mergers. If you divide the sample into large galaxies and small galaxies, then the merger role of merger, or maybe the contribution from merger events, are higher for larger galaxies. That makes sense. When we published this result, we were puzzled. Maybe this was because, I mean, this, what do you mean by this? I mean, mergers not playing dominant role. Maybe it's because we have only cluster environment where galaxy mergers are relatively more difficult. So now we turn our heads to the Horizon-AGN simulation, which has not only cluster regions but also sparse field regions. So now we have many more galaxies from Yohan Dubois. I once again emphasize that cluster simulation YZiCS was based on the same baryon physics recipes as Horizon-AGN, so we can compare them. So now this is Horizon-AGN versus more recent IFU survey data. The lambda epsilon diagram for all galaxies now. Atlas 3D data are in pink, and then the Horizon-AGN are in shades. So now, if you remember my cluster sample was actually more rounder and slower rotating than this Horizon-AGN, simply because Horizon-AGN has many more field galaxies, field early type galaxies. By the way, now I'm showing you only early type galaxies by G-R color, because predominantly most of the IFU data are early type galaxies. And now if I divide the sample into high mass and low mass galaxies tend to be more slowly rotating than low mass galaxies. So the slow rotator fraction in the high mass sample is about 30%, whereas in the low mass sample it's only about 4%. So if you take the whole sample, the slow rotator fraction is roughly about only 15%, precisely as observed by many other different surveys. This paper has been submitted 2 weeks ago. And now, we are curious about the mass dependence because IFU study has said that there appears to be some mass dependence. So this is a lambda spin parameter versus stellar mass of galaxies. So the shades are from Horizon-AGN early type galaxies, and then red curve is the mean value as a function of stellar mass. So the thing is, our investigation starts from 10 to the 10 solar mass, but we find it rather difficult to reliably measure the spin parameter for smaller galaxies, simply because we do not have really enough number of stellar particles. So we focus on this negative slope, and then typically, what is this? That's capillary. That's so Atlas 3D data now show you the slow rotator fraction, which is rising fast as a function of stellar mass, and that's actually reproduced by this Horizon-AGN rather nicely. Okay, and I would not really trust anything below 10.5 here. And then this is a density parameter. D5 is the distance to the fifth closest galaxy. So the denser region on the left and sparse region on the right. And then now, if you plot lambda, it's only a small slope. And then slow rotator fraction shows almost no dependence in density much. And these are all qualitatively consistent with semi-data. And then, now go back to the importance of mergers. What role did mergers have? To study this more efficiently, I divide all these Horizon-AGN early type galaxies into 4 groups. The first by the virial halo mass. So these are the groups and clusters of galaxies above 12.5. And these are field galaxies, or maybe very small groups, tiny, like local group. Okay? And then 200 something central galaxies in these large groups, and then 3,000 satellites in large groups. And centrals of these small groups, and then non-centrals, sometimes they could be isolated, sometimes the field normals. And then I show you the major and minor merger frequency. So the group central galaxies in large groups, they had actually a fair number of major merger and minor merger since redshift 1. Typically about 2 major mergers and about 5 minor mergers. The central galaxies of small groups, they also had about a couple of major mergers and a few minor mergers, consistent with large group centrals. And then satellites barely had any mergers. They are just focusing on 0, 0. So they usually had about typically 1 minor merger, but 1 or none major merger satellites. All right. And then I now show you lambda epsilon diagram for these 4 subgroups. Group centrals predominantly slowly rotating because they had many mergers. Field centrals in smaller halos, they also have a large fraction of slow rotators, 40%, because they too had a large number of mergers. But now if you look at satellite galaxies in large groups and satellite galaxies in small groups, and now they have wide variety of spin parameter, and now most of the fast rotating galaxies are not the central galaxies in groups, right? So now I get more curious about this phenomenon. So now I measure, because probably merger is not explaining everything about spin down history. So now I measure perturbation index like this. So if you have flyby or maybe something in the neighborhood, then your galaxy will feel the torque, and then there will be impact on your spin, right? So we measure the perturbation following Bird and Howard. And then the perturbation, larger value means now throughout the cosmic history, there was more perturbation due to neighboring galaxies, okay? And then the lambda change, delta lambda, I show you 2 specific subsamples. They are the galaxies that did not have any mergers. So now they are free from merger effects. No merger galaxies, but the top 1,500 galaxies are the satellite galaxies in group. And the bottom are 2,000 galaxies in the field, all right? So they have some environmental effect, and these ones, we don't expect any environmental effect. And if you look at the top one, yeah. So if you have higher P, higher perturbation, that means if you had more neighbors, and then the spin down will be greater. Okay, so P actually is doing something. The perturbation is doing something on spin. If you look at the down panel, then these field normals that did not really have any merger and did not have many companion galaxies throughout the cosmic history, they still show some spin down almost as much as a 0.1, but there is no dependence on perturbation. So these galaxies know how to spin down regardless of merger, regardless of environment, for some reason. We wanted to pin that down, but we are still puzzled. So higher P, more spin down in denser environment, but if they are really outside dense environments, then they spin down just a little bit due to some reasons, maybe star formation and so on. And this sums up what I have just said. Again, Horizon-AGN early type galaxies in large halos on the left and in small halos on the right. The top ones are the central galaxies, down ones are the satellite galaxies. And then central galaxies, they spun down very quickly in the early universe before redshift about 1 due to multiple mergers in the early universe. Okay. And then satellite galaxies do not show the same thing. Satellite galaxies in large clusters spun down quite a bit in the recent universe, probably when they were becoming members of larger halos, mainly through the perturbation. And the field normals, they knew how to spin down very, very slowly, without much obvious perturbation or much obvious mergers, like this. And if we illustrate the impact of mergers and versus the impact of perturbation, when I say perturbation here, I mean non-merger thing. I don't know exactly what we are measuring using those perturbation index, but it's something other than obvious mergers. So merger versus non-merger. So this is the fraction of absolute spin down for all these tens of thousands of galaxies by merger. So central galaxies in high density regions, most of them lose their spin through mergers, 80%. Most of them lose their spin through mergers. And the central galaxies in smaller halos, too, they too lose most of the spin through mergers because simply they had more frequent mergers. But all the rest, so satellites and isolated galaxies, they would cause spin, have spin down not by mergers because the merger contribution is smaller than about 40%. Most of the spin down will be coming from non-merger phenomenon. So the simulations suggest, I would say, spin can be finally understood realistically through simulations. And if we focus on the massive early type galaxies, they have spun down globally everywhere, and since redshift about 2. I'm going to get back to that in a minute again. And if we focus on central galaxies, that are roughly about 15% of our classification, and then mergers dominate spin down, as many of the previous theoretical suggestions made clear. But satellite galaxies that are dominant fraction of realistic universe galaxies, and then they actually spin down through perturbation rather than mergers. But that's a unique claim from my group, and there are roughly about 5 or 6 groups working on the spin evolution of galaxies through simulation, and we are the only one suggesting that it's not really mergers that cause spin down. So I'm really worried about the referee report. All right, so now the issue is resolution good enough to study spin? Right, that's a question. So maybe some of you with hawk eyes have noticed this before. For example, in Horizon-AGN versus Atlas 3D, Atlas 3D has many more fast rotators, the red dots, right? Whereas model galaxies are rounder and slower rotating. And if you look at Zephyr Penoyer's work, Illustris shows the same thing. Atlas 3D has many fast rotators. Illustris doesn't really have fast rotators. And I'm not showing you the Eagle here, but if you look at Eagle, almost all of the brightest cluster galaxies, BCGs, are fast rotators in Eagle simulation. And in IFU study, almost all BCGs are slow rotators. So there is some problem with simulation. We are lacking something, and maybe we do not have good enough models to tackle this sensitive issue. And this explains a little bit. So this is the realistic galaxy, NGC 891. If you look at Wikipedia, they say this galaxy probably is similar to Milky Way. They say so. And the vertical scale height is about 300 parsec. Whereas the force calculation resolution in our simulations is about 1 kiloparsec. So resolution is 3 times bigger than the scale height. So maybe we can't really reproduce the rotational motion very well. So New Horizon started as a result. So now high resolution cosmological zoom-in simulation, mainly led by the IAPE folks, Yohan Dubois is there. And it's a 10 megaparsec sphere inside 100 megaparsec Horizon-AGN sphere. So the volume-wise, it's about 1,000th of the Horizon-AGN volume. And the resolution is about 25 times better. So the Eagle, Horizon-AGN, and Illustris all share similar maximum resolution of about 1 kiloparsec. But now we have 40 parsec. Stellar mass resolution is about 10 to the 4 solar mass. and with some improved physical prescriptions. The first part of the simulation was performed at IAPE, and second part at Yonsei with me, and the third part is now continuing at IAPE again. We have come to now about redshift 0.8 after 30 million hours. So, thanks to Sebastian, who must be somewhere over there, Sebastian found match catalog between Horizon-AGN and New Horizon. So we found the same galaxies in two simulations, high resolution New Horizon, low resolution Horizon-AGN. They are the same galaxies at redshift 1. Edge on view, face on view, sorry. So now we can do something better. That should be obvious. And this is our, can I lower the light a little bit? So this is our skirt image. So this, we made mock images doing radiative transfer on post-processing wise using skirt software. Right. So that's the edge-on view of this one galaxy at redshift 1 made by my student, and this is face-on image. So, I mean, Horizon-AGN was great, no doubt, but I think this is actually getting substantially better. And then another student of mine, Minjung, should be here, but not. I think they know where heaven is. The heaven is where their boss is not. So this is this shows you a typical history of merger of primordial galaxies that makes a large Milky Way-like galaxy at redshift 1. Okay? And then on the right, you see the circularity index for the all stellar particles that are within this video region. So now you have like 1 million stellar particles here in this circularity and radius diagram, radial distance diagram. So initially now you have about 10 galaxies merging to be a primordial galaxy at redshift about 3.7, and now it's chaos. If E is 0, that will be random motion, pressure dominant, and then if E is 1, there will be a clean rotating disk, and if it is -1, it will be counter-rotating disk. At redshift 3 now you have a total mass, and now I turn the time on and see how chaotic the formation process of galaxy is. And I watched this on 20 different galaxies. They're all like this, just complete chaos. And then see at redshift of 1.8, now you begin to develop thin disk. See, thin disk. And at redshift of 1.5, you have a very, very handsome disk. So this is totally against what I learned in the textbook. In the textbook, I learned because the initial net angular momentum can't, over collapsing cloud can't be exactly 0. So all the first galaxies should be like disk shape, and later through mergers, they will turn into spheroidal galaxies. That's what I heard, and that's what I teach my students. But that's not what I see here. Initially, galaxies are chaotic. They may tell you the large dispersion value, but not because they are virialized through some sort of relaxation, but because they are chaotically bumping to each other. And then only much later, redshift at about 0.5, 0.6-ish, now it begins to develop a handsome disk, and then after that, disk grows, if you believe this simulation. Because this is fun, I'll show you again. See how chaotic the early history is. And then at redshift about 2-ish, now you begin to see some development of a disk. And yeah, 2-ish, it's 1. Now, whenever you have a new galaxy coming in, now you see some new streak in phase-space diagram. And now you see 1.5, you have a really well-developed disk. And if you look at this diagram again, I mean, this movie once again, look at how disk gets developed. Initially, there is no disk, chaos. And then at some point now, rotating disk. See, you see, and then ring, big ring, and you begin to see a bar at the center. Initially, bar rotates with the disk, but later it turns the direction opposite. Whether this is to be trusted or not, I don't know. I'm not a dynamicist. But something really much more complex than what I learned from the textbook is visible here. So the prospect is now, we have now new horizon. Probably with this new horizon, thanks to Yohan, we can see further ahead. What was invisible previously, now this will be possible. And yeah, with this, obviously, you know, I just only talked about spin, but like the formation of disk, and we measured the disk scale height of thin disk and thick disk. Mysteriously, all these redshift 1 disk galaxies have really well developed disk, and then it is best fit when we use 2 exponential disk with thin and thick disk. And thick disk scale height is about 3 times larger than the thin disk scale height. In Milky Way, it's about 3 to 5 times. It's not too bad. So development of disks and morphology transformation, that was obvious in the movie, and so on. So I'll end my talk with one of those large galaxy images at redshift 1 from New Horizon simulation. Thank you very much.
These are beautiful simulations, beautiful images. I wonder if you could compare these pictures of disk formation with the story that's told by Gensel on the observational side, Deckel on the theory side, about huge compactification effects, many clumps in disks at redshift 1 or 2. I see nothing like that here.
I haven't looked into that, but I will. So what scale are they?
These are 10 to the 8th solar mass type massive clumps.
We see a lot of them. I don't know whether this image is good, but some of these galaxies, sometimes on the disk, and also away from the disk as well, because the merger history is so complicated. And I try to measure their stellar mass. There are a whole bunch of them, typically about 30 such small stellar systems of mass between 10 to the 6 and 10 to the 8 solar mass. I don't know whether they are comparable to the thing that's claimed by them.
You were talking earlier about how you think one of the worries with the current simulations was that because we're not resolving the scale heights of the disks so well, there might be some problem there. But I mean, you were talking about the spin down of early types, which aren't really disky, right? So they have a much higher intrinsic height. So why do you, could you comment on why you still think that's important?
What I'm saying is, if an early type galaxy has a disk component, and it seems almost all early type galaxies have a disk component, and that component is not being resolved. Yeah, the dispersion component probably is okay, but the disk component is not resolved. And so probably I can show you somewhere. Okay, I'll give you one example. So this is not particularly an early type galaxy, but if you measure the bulge to total ratio on the same galaxy, but New Horizon galaxy will give you bulge to total ratio 0.4, whereas the Horizon-AGN will give you 0.7. So just measurement is impossible with poor resolution data.
Nikos, wait for the microphone.
So the two disks you are finding, the thin and thick disk, you say they can fit them a double exponential and you find it naturally. So do you have any idea of the origin of this? Why, how do they appear, and why do they have this clearly distinct geometrical behavior?
That will be our next paper. Yes, because what we are doing is we are coloring all the stellar particles that belong to thick disk component and that belong to thin disk component. And because we are coloring them and we have a particle IDs, we know where they have come from. So maybe we can talk about the origin of this thick disk.
But you color them according to what criterion?
Yeah. What criterion?
Yeah. In the end or the beginning? Do you know from the beginning when a particle will be in the thick or the thick disk or what? How do you know that? In the beginning of your your simulation when you start doing particles, creating particles?
I'm not sure if I get your question correctly.
You mean the particles, you say you color them
Yes.
in the end of the simulation?
Yes.
Not during the
Not
simulation?
during.
During the simulation?
Yeah.
So how do you know where some particle belongs to the thick or the
Because
thin?
we identify all the halos, right? So if at redshift 1 we have one large galaxy, we know their origins. We know the stellar origins. So if you have a thin disk developed, or maybe a disk developed at redshift 1, you know where these stellar particles came from. In situ star formation, or maybe came from that small galaxy or that other small galaxy, and so on. So we can see, for example, the origin of thick disk has been discussed a lot, right? So dwarf galaxy, going through the disk and so on. That can be addressed. And this is the level of fit, as I mentioned earlier. So this is the vertical fit with two exponential disks. This is thin disk and thick disk component. This is too good, right? If anybody comes with the observed data with that kind of fit with just simple exponential function, I would not really believe it. But the simulation data are almost as good as observational data on some cases.
Sukyoung, if we can come back to your earlier simulations in clusters,
Yeah.
and you show the evolution of lambda, it seems to me that there was bimodality in the distribution,
Yes.
right? So I'm pretty convinced of your scenario where you have the satellites and the mergers, but in the cluster, yeah, you see at redshift 0,
Yeah.
it's clearly bimodal.
Yeah.
Whereas I would have assumed that, if you're sampling from a sort of log normal distribution of lambda,
Yeah.
you will end up something quite continuous. So what's the origin of this bimodality?
This bimodality of lambda is not visible in the observed data. I don't know why. We know why the two sequences happen. It's mainly through mergers in the early times. And once they become very heavy and slow rotator, then chances are they will not really return to fast rotator very easily. But the bimodality is much clearer in simulation than in the observational data. I don't want to say that in observational data, it's very difficult to know the membership perfectly. And also there are lots of complications. But if I did that, then it'll be viewed too arrogant. So probably keep this off the record.
Is there any more question? Okay. I may ask one.
Sure.
There is this amazing data from Pierre-Alain Duc about a very deep survey around the early type galaxy, where for some of them we see a very extended disk far away from the center. And should that change the picture of the spin evolution of early type galaxy if we are able to measure the rotation in the outskirts so far away?
That's an excellent question. So if you look at this diagram, this is model galaxies, and we measure the rotation profile out to 3 virial radii. And if you look at IFU study, to my best knowledge, most of the IFU data are within 1 effective radius. The SEMI on cluster, closer galaxies, SEMI reaches out to about 2 effective radii, but for most of the galaxies, it's about 1 effective radius. But a lot of angular momentum is now actually stored outside 1 effective radius. So to do a realistic study, you really need to have observation on outskirts. So a few months ago, the SEMI folks have sent in the proposal to use MUSE to measure the lambda to like 3 effective radii on some galaxies. I don't think they got the time though, but that kind of comparison is something really very important, and I'd like to compare the models with.
Okay, so if there is no more question, okay, so we should thank Sukyoung again.